Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. So we are almost at the end of the week number 7 of this NPTEL course, and we are well underway into designing algorithms that can drive autonomous systems such as the satellite orbiting the Earth that we see in our background. So what we were looking at last time was a new sort of topic on design of adaptive controller in the case of unknown control gains. Okay, so um, so the design procedure was more or less similar, right? The only difference being that there was a gain attached to the controller, which was not the case in all the adaptive designs we saw earlier, right? And uh, we of course had the usual tracking objective, right, that we take, and then we made some pretty reasonable assumptions on this boundedness of the function f, and b being non-zero, which is essentially translates to controllability of the system. With the error dynamics in place in the form of equation 1.3 here, we started to do our design by actually applying some nice little tricks so that we redefined the parameters of the system into theta 1 star and theta 2 star, starting from A and B, right? And we of course designed the known controller. From this, we actually moved to the unknown controllers simply using the certainty equivalence principle of replacing the unknowns with their estimates, right? And we started with our Lyapunov analysis with this new control design, right? Now, we started with a standard Lyapunov function, which involves taking the known case Lyapunov function and adding quadratic terms corresponding to the unknown parameter. But we quickly realized that this leads us to the non-implementability issue, where the unknown parameter itself starts to appear in the update log, right? So which is absolutely not allowed, because that is essentially what we are trying to compensate for. Yeah. So we tried a different Lyapunov function, which is of course well known in literature, and we simply added an absolute value of b in the Lyapunov function. And what we saw was, instead of the parameter itself appearing in the update log, the sign of the parameter appears in the update log, which leads us to an additional requirement for adaptive control for unknown control gain systems. And this requirement is that we need information of, I apologize, we need information of the sign of b. All right, so this is sort of a critical requirement which we cannot do without when we are looking at unknown control gain problems, right? So as I mentioned, if there is a solution that one of you can find which does not require us to use the signal or the sign of b, then you would have done something exceptional, right? And well, as of now, it seems impossible, is what I would say, is how I would put it. Okay. Now, we of course we get a negative semi-definite v dot, and we can complete the proof using standard signal chasing and Bablat's lemma corollary type arguments. Of course, remember that in order to complete the signal chasing arguments, we need boundedness of various quantities. And this is where uh, the boundedness of f required. Yeah, so the boundedness of f will be required in order to complete these signal chasing arguments. All right, so this is where it gets applied. Although we stated the assumption and we solved the whole problem without seeming to require it, but that's not true. When you try to do the signal chasing argument with complete diligence, specifically when you try to prove that E dot is in fact bounded, you will need the boundedness of this function. All right. So it's not like we made a frivolous assumption. We will need to use this assumption, okay, in order to complete this proof. So I do recommend that you complete this proof. Yeah, I do recommend strongly that you complete this proof so that you can understand sort of what kind of assumptions go into the completing the proof. Yeah. All right. So now that we have completed this discussion on the unknown control gain, and we've already done the problem of unknowns in the drift vector field, or the unknowns that are connected to the states. We are ready to look at this generic model reference adaptive control problem for linear systems, right? So this is where we will begin today. So I will mark it as lecture 7.6. All right, I'll mark it as lecture 7.6. So what is model reference adaptive control? This is a paradigm, if you may, in adaptive control, and a rather you know important and occupies a very large place in adaptive control literature. Yeah. So the idea is I start with a linear system, which is x dot is ax plus bu. So I hope all of you have seen linear system models such as these. Yeah. And of course, now we are dealing with vectors. We're no longer looking at simplifying, or well, not necessarily simplifying, but scalar systems and double integrators and things. We are looking at a linear system. First of all, we're not looking at nonlinearity. There's no fxt, but we are looking at a vector state x in Rn. Control is in Rm, so the dimension of the control is possibly smaller than the dimension of the state. And of course, you have this x dot is ax plus bu, so not necessarily double integrator or anything like that. Okay, great. So here, instead of x trying to follow some r, right? So that's the typical thing, right? X following r, or x goes to r as time goes to infinity, is what we have been looking at until now. So instead of that, what we say is x has to follow xm, and xm is generated as an output of a reference model. All right, so xm is coming out of a differential equation, okay, or as an output of a reference model. Yeah, so physically you can think of there being a reference model in which there's an input signal and there's an output, and your system output is sort of tracking this. All right, so if I well, let me see if I can, if you want to think of it as a block diagram, let me see how this will be. So usually you have a reference here, so this will be let me make this bigger first. So usually I will have a reference here, right? And then I will have some kind of a control block here. Okay. Then I'll have a plant block here. All right. Then I'll have something like an output, I suppose, right? And this output, of course, feeds back. Well, actually, not this output, but typically you will have this going here. Yeah. And of course, because it's an adaptive controller, there will be an adaptation block, right, which will also take this input. Yeah. And possibly also this input. And the output from this goes here. Okay. So, and here something more complex happens. You have an input system and there is an R, right? So this is basically the reference plant, right? So this is something like a reference plant. I will probably write it here, governed by AM, BM. So this is the reference, right? This is the XM with the plus minus here, right? And then you have something like a control here, U, right? And then you have the plant here, which is given by AB, is the plant itself. You have the adaptive block, which is A hat, B hat, if I may. It's crude, it's a crude form, but this is how it will look. All right. So this is like a how this adaptive control block will look, because the plant matrices AB are also not known. So I'll create an adaptive law for that. That will also feed into the control. Then there's a reference system which takes in a reference R and outputs what the system needs to track, which is this X sub n. All right. And then all of it comes together to give you the control, and the control then of course feeds into this guy. Okay. So that's how this model reference adaptive control block diagram will look like. Yeah. So that's the big difference here. Yeah, and of course, as usual, we assume that this reference input is bounded and smooth and all that stuff. Okay. We also assume there are several assumptions. Maybe I should mark them. So bounded and smooth. AM is assumed to be Hurwitz. So basically for the reference system, it has to be a stable reference system. So the matrix AM is a Hurwitz matrix. AN and BM are assumed to be known and the same dimensions as A and B. Okay. So, and of course, A, B are unknown constant matrices. Okay. So A and B are assumed to be unknown. So these are the quantities that are not known. So this linear system is essentially unknown, and you're trying to figure out what this linear system is, or at least you're trying to compensate for the fact that you do not know this linear system. Okay, so you literally do not know this linear system, but of course there are a few other assumptions. I mean, we will come to the assumptions. Yeah. So, but these are the assumptions on the reference system. Yeah. So anything that you want to track has to take as input a nice bounded smooth signal. So this is just standard assumption again to ensure that the reference signal that or the XM that you're trying to match comes out to be a nice enough signal. Okay. And then of course we assume that AM is a Hurwitz matrix, which ensures again stability of the whole system. So there's a bounded input Hurwitz matrix, so output will also be bounded. Okay, this is standard and well-known result in linear systems, that if you have a stable system which is perturbed by some bounded input, then the output is also going to be bounded. All right, so that's what we get. All right, great. So now what we want to do is drive X to XM, and we do not know matrices A and B. Okay, now the question is, well, actually the first question that we ask is what kind of assumptions are required. Yeah, so we've already uh, put in several assumptions on the reference, but we also need assumptions on A and B, or the original system for that matter. Yeah. And so what are these assumptions? These assumptions are of course called the matching conditions in model reference adaptive control. You're already used to matching conditions. That is, when you want X1 to track R, you want X2 to track R dot. in a double integrator system, right? So this is also a matching condition. So we have such similar matching conditions here. The first is that the pair AB has to be controllable. This is not exactly a matching condition, but we are clubbing it loosely under matching conditions. Yeah, because if the pair AB is not controllable, there is no scope of designing controllers for this system. Okay, so this is more like a necessary condition for us to be able to do any control problem or solve any control problem. Okay, so the first is AB has to be a controllable pair. This implies that if I'm given any matrix P in n by n or n by n matrix P, there must exist a matrix K such that A minus BK equals P. Okay, so what does it mean? So A minus BK is coming how? So this is when U is chosen to be minus KX, right? Which means that, so controllability, as you would already know, I hope. If you don't, I really urge you to go back and revise what is controllability for a linear state space system, right? So what it means is that if AB is a controllable pair, then given any matrix P such that I want the system to look like x dot equals px, then I can choose, I should be able to find a k in k such that u equals minus kx does the job. So if I put u equals minus kx, this becomes a minus bk x, right? And so I have my desired system. Okay, and now notice that um, what we try to match are not the matrices themselves. Okay, so notice very carefully that this assumption does not guarantee that the matrices A minus BK and P match. No, they just ensure that the eigenvalues of the two matrices match. Okay, so this is called standard pole placement, if you may. I mean, this is, I would say, called pole placement, or in time domain it's called eigenvalue assignment. Okay, this is called pole placement or eigenvalue assignment. What it means is we are not really going to be able to match two matrices. Yeah, but what we, so that not every entry of the matrix might match, but what matches is the eigenvalues of the matrices. Okay, so this is called pole placement or eigenvalue assignment. So this is possible whenever A and B are a controllable pair. If you do not know what is controllable pair, please go and revise. Right? Great. So that's the first condition. Great. So now the next assumption actually makes this sort of more stringent. It says that there exists a K star, again an n by n matrix. Let's see. Yeah, there exists a K star, an n by n matrix, such that A minus BK star is exactly equal to AM. Okay, so now we have made it stringent, right? So this is where it is different from point, because point A1, because we are not just saying that the eigenvalues are matching. No, we are actually saying that the two matrices match. Okay, now there is much to be said about the assumptions that we are making. They are restrictive in several scenarios, and one might ask, why should it's pretty reasonable to say that AB is a controllable pair, because without that, control is not possible, and therefore that eigenvalues of these two match. Very reasonable, because we already said AM is Hurwitz. I can do any pole placement if AB is a controllable pair. Therefore, matching the eigenvalues of these is obvious, right? So matching of eigenvalues of both is obvious from assumption A1, right? It's obvious from assumption A1. Okay, but we are talking about something more. So now why a lot of times we are okay with this assumption A2 is we somehow say that um, uh, we have flexibility in choosing AM a lot of times. Okay, because we are not always specifying AM very stringently. Yeah, the user or the designer, sorry, the user may not specify AM that strictly, because in most cases we are interested in pole placement only and not this AM matrix itself. So it's very possible that you will be able to choose AM such that the eigenvalues are consistent with what the user wants, but it also ensures this kind of a matching happens. Okay, so sort of a justification for this assumption. Okay, we are not saying that this is without any flaws or anything. These assumptions have a lot of flaws, but again, these are the only conditions under which solutions exist. Okay, so what is the justification? It's that flexibility in choosing AM exists in real problems. Okay, more often than not, there is flexibility in choosing the same. Okay, and that is why such a condition may be digested. All right, may be digested is what I would say. Yeah, otherwise it's not. Okay, all right. So let's look at the next one, right? The next assumption A3 requires the existence of an L star such that BL star is equal to BM. All right. Now again, remember that because I do not know A, I cannot have a knowledge of K star. I hope that's evident. Okay. So what we are doing by this trick is actually again redesign or reformulating our parameters. We are going to move from parameter A to parameter K star. Okay, so that's the idea. So we don't know A or B in fact. So we don't know K star actually. Okay, so let's sort of, I hope that's evident. Right, great. So now this next assumption is something again similar or along same lines. It says BL star has to be equal to BM. So there should exist a L star such that BL star equals BM. Okay, so again the justification is similar, and it is that there is a flexibility in choosing BM. All right, there is some flexibility in choosing BM. So yes, these assumptions are to be taken with a pinch of salt. Yes, I agree that these assumptions are very restrictive, but these are the sort of justifications under which we operate. Yeah, in fact, without this, again, solving model reference adaptive control problems is impossible. Okay, not known. Yeah, without these assumptions. So this is sort of what uh, are the restrictive or the restrictions of the solution that we can provide. Okay, so so another part of assumption 3 is also that L star has to be symmetric and sign definite. Okay, so another part of the assumption is like L star is to be symmetric and sign definite. So the way to think about this on top of talking about flexibility in choosing BM is that somehow we are saying that BM is the has similar definiteness properties as B. All right. So if I multiply B by, for example, a positive definite matrix L star on the right hand side, and I get a BM which has no specific properties or anything, because BM is not required to have any specific properties, then if you think about it, then this is almost might be identical to um, doing some kind of a nice group operation on B itself. Okay, so there is if I just think of a very simple or the simplest situation. Okay, let's think of a simplest situation where, let's see, simplest situation. Okay, let's think of L star as some epsilon identity. Okay, some epsilon scaled with identity. Very simple situation. So what is Bm going to be? It is going to be epsilon B. Okay, it's going to be epsilon B. Okay, so this is the sort of again the argument which um, gives us some hope that this kind of an equality can also be justified, right? So if L star is very close to the identity matrix, then Bm is almost similar to B itself. But again, remember, Bm and Am are known, while B and A are unknown. Okay, all right. And also remember that in typical adaptive control, we do not claim anything about being able to identify the parameters exactly or uniquely. Yeah, we only claim to be able to compensate it and guarantee tracking. Okay, so we have made these assumptions, right, which are suitable for us to do this model reference adaptive control design. And we'll go on to do a design, and of course we'll prove some kind of a tracking of X with XM. So X goes to XM is what we'll prove asymptotically, right? But of course we'll not be able to claim that K goes to K star or L goes to L star, because our new parameters become this K star and L star, right? So these become our new parameters, right? And we will sort of compensate for the effects of this, of not knowing this K star and L star. Okay, so that is essentially what will happen. And of course we assume that L star is symmetric and sign definite also. So it's more assumption on this L star. So several assumptions. And on top of this, just like the scalar case, in assumption 4, right, we also claim that we know signum L star. Okay, remember, in the scalar case, we required the sign of B to be known. So L star here actually serves like serves to quantify the same thing. So we require the signum of L star. And what is signum of L star? Because L star is a matrix, correct? So what is the signum of a matrix? That's defined here. It's defined as +1 if the matrix is positive definite, and it is defined as -1 if the matrix is negative definite. All right. So these are the sort of assumptions we have. I mean, I just wanted to start off uh, this session with trying to understand the assumptions. Yeah. First, we have the controllability assumption. Then we have the assumption on A and AM matching via this condition. Then we have a B and BM matching via this condition. Not just that, the matching matrix has to be symmetric and sign definite. And further, we also require to know the sign of this matching matrix. All right. So that's it. So what we saw today is essentially a sort of a setup of the model reference adaptive control problem, which is one of the most popular and famous, and occupies a large space in adaptive control literature. A lot of adaptive control literature has developed around model reference adaptive control. And we just saw the setup, we just saw the assumptions today, yeah, in this session. And what we plan to do in subsequent sessions is to analyze and design adaptive controllers for this system. We also understand, we take everything with a pinch of salt. We understand that these assumptions may not always hold, but we also understand that adaptive control is not going to actually identify the parameters in several situations, but simply try to compensate for these unknowns. So In spite of the fact that these assumptions may not always be validated in several circumstances, these kind of model reference adaptive controllers work very well. In fact, they have been flight tested on fighter jets, so they have been functioning rather well for several decades now, and they actually give good real performance. And one of the few nonlinear controllers which have actually been implemented in the industry. Great. So this is where we stop today, and we'll continue again in the subsequent session. Thank you.